Here we're going to continue with this Kohn-Sham method and the decomposition of the universal functional. In the previous video, we were centered analysis on the kinetic energy functional of this fictitious non-interacting system. And here we are going to center more on the decomposition of the Hartree exchange and correlation energy. If you remember, in this Kohn-Sham method, we were separating or decomposing the total energy function in two terms. In the kinetic energy functional of this non-interacting fictitious system and this Hartree exchange and correlation energy functional. So basically that Hartree exchange and correlation energy is going to be like the difference between the complete and exact energy function that of course we don't know minus this kinetic energy functional of this non-interactive system that we defined before. Okay, now actually this Hartree exchange and correlation energy, it's actually decomposed in different terms usually and have a different expression. So we're going to analyze how this term is usually decomposed here. So as a first step here, the Hartree exchange and correlation energy is decomposed in these two terms. One is called the Hartree energy functional, and it's expressed in this way, EH, and the other one is the exchange and correlation energy function. So let's first go with the Hartree energy function. The Hartree energy function is defined in this way. Actually, this is not the first time that appears this Hartree energy function. When we consider the Hartree approximation for the uniform electron gas, we had another term which was the same as this one. Actually, it has like a classical understanding of this term. It's basically is the classical electrostatic repulsion energy for this charge distribution. So we can classically understand this Hartree energy. Okay, this is one. This is the Hartree energy. Now let's go to the exchange and correlation energy. It's actually usually decomposed in two different terms, the exchange energy and the correlation energy. So we're going to analyze which is the exchange energy and what's the correlation energy next. So the exchange energy is defined in this way here, Basically is the average of the electron-electron potential energy when we are considering the Kohn-Sham wave function minus the Hartree energy that we have just described before. So let's remember that this Kohn-Sham wave function is a Slater determinant associated with this non-interacting fictitious electronic system. Actually, this exchange energy, it also appeared when we considered the Hartree-Fock approximation for that uniform system. So in the Hartree-Fock approximation, we're considering to describe that complex interacting system. We're considering that the wave function within that approximation could be described as the wave function for the non-interacting system. So we're using the Slater determinant. So in the Hartree-Fock approximation, we're using the Slater determinant. And when we were analyzing the energy associated to that electron-electron potential energy, considering that Slater determinant, it appeared within this Hartree-Fock approximation, it appeared like two different terms. One was called the exchange energy, and the other one was the one we called the Hartree energy. Actually, the same one as the one we defined before. Actually, therefore, within the Hartree-Fock approximation, we also had the exchange and the Hartree energy. So here what we are doing is within this Kohn-Sham wave function, actually the kind of approximation we are doing is actually very similar, because we are using here a wave function which is a Slater determinant. And considering that Slater determinant that actually we call the Kohn-Sham wave function, and calculate the electron-electron potential energy, the average of the electron-electron potential energy, the total one, and you subtract from this one the Hartree energy, the one which is remaining is what we called within the Hartree-Fock approximation, we call the exchange energy, and the same is the one that we are having here. Besides that, because this is not all, of course, this kind of approximation that we did already in the Hartree-Fock approximation, we're using the wave function corresponding to this non-interacting system. Of course, the real system is the interacting one, so the real system is going to have a wave function that's going to be very different from this Slater determinant. So this kind of Hartree-Fock approximation, or just considering the exchange and the Hartree energy, is not going to be the end of the story. And therefore there is something which is remaining here. And what's the remaining one? The remaining one is the one we are going to call the correlation energy. So, but what's the correlation energy? So basically it's the rest that we have not considered up to now. So, and what is the rest? So basically the correlation energy is defined this way, is the average of the kinetic energy of the electrons and the electron-electron potential energy when we are using here the exact wave function of the real system. That will be the exact wave function of the real system. So therefore this one will be like having, of course, the exact energy. So if we subtract from here the one that we have considered, I mean the average of the kinetic energy plus the electron-electron potential energy, when we are considering this Kohn-Sham wave function, if we subtract this one, that what we are going to call the correlation energy. And as you can see here, the correlation energy, it includes like two different contributions here. One is coming from the kinetic energy and the other one is coming from the electron-electron potential energy. So this correlation energy contains a kinetic contribution and it also contains a potential contribution. The kinetic contribution basically is the difference between the average of the kinetic energy when you consider the exact wave function of the real system minus the average of the kinetic energy when you consider the Kohn-Sham wave function of this fictitious non-interacting system. And again, the potential contribution to the correlation energy is the difference between the electron-electron potential energy when you consider the exact wave function minus the average of the electron potential energy when you consider this Kohn-Sham wave function. So here we have described the different decomposition that it's usually can be applied to the this term here, this Hartree exchange and correlation energy, where basically it's usually decomposed as the Hartree contribution that we know how it looks, the exchange contribution that we know how to calculate that, and then the correlation energy that's going to be a function of the density, but of course no one has an accurate description for that function. At some point we probably need to, well, of course for sure we are going to need to make any approximation for that functional here. So here we have analyzed different decompositions of the universal functional within this Kohn-Sham method, and the next is going to we need a method to describe and to get the Kohn-Sham wave functions that appeared in the kinetic and either in this kinetic energy functional and also in this exchange contribution to these Hartree exchange and correlationality functions. So we need a method to get that Kohn-Sham wave functions.